Hello, I welcome you all in this course on refrigeration and air conditioning. Today we will take up the concluding part of cooling load calculations, cooling load 3. In this part, today we will solve one numerical, and in fact we will design a air conditioning system for a restaurant. So in this problem, first of all, total infiltration air is 250 CFM. Because we have buildings which are not airtight. Further, in a restaurant, the customers, they frequently come inside and they go outside. So there is a lot of infiltration. So this 250 CFM of flow inside a building has to be converted into equivalent liters per second. 100 CFM is equal to 47.195 liters per second. This is the volumetric flow rate of air inside the restaurant. And this air which is entering the restaurant is at ambient condition. This is ambient air which is coming into the restaurant. Now the restaurant is maintained at this temperature and air is coming from the outside. Definitely this air is bringing in latent heat and sensible heat on the refrigeration system, air conditioning system. This is sensible heat. So in order to find load on air conditioning coil, first of all let us find out how much sensible heat and latent heat is contributed by infiltered air. So in order to find that, first of all, we will convert CFM into kgs per second. So 250 CFM is equal to 100 CFM is equal to 47.195 liters per second. So 250 CFM is going to be 47.195 divided by 100 multiplied by 250, and that is going to be equal to 117.9875 liters per second, right? Now this liters per second has to be converted into the kgs per second. This we will do later on. Let us go through this problem. There is a solar heat gain through glasses. So in any building, the entire building is not opaque. Part of the building has fenestration, and this fenestration is mainly consists of the glasses, and the solar heat gain through glasses is equivalent to 2 kilowatts. Total heat through opaque part means walls, ceiling and floor of the building. Now in a building, when the solar radiations falls on the building, they fall from all sides. They are direct radiations and diffuse radiations, and heat transfer also takes place through the floor also, because outside temperature, let us say 42 degrees centigrade, inside temperature is 22 degrees centigrade. There is a temperature differential and heat transfer through floor also takes place. And especially in the case of winter, when outside temperature is low, inside temperature is high, the floor temperature goes down drastically, and that is why in the building, when the floor heating is done, that is the best kind of heating in a building in winters, when floor heating is done. Because I told you earlier also, the heating should be done on the lower half of the body. Cold air should blow on the upper half of the body. So when the floor heating is done, subsequently this heat heats up the other articles kept into the room, other objects kept into the room, and a person who is occupying this room gets the feeling of comfort. So here in this case, because this is summer air conditioning, so in this case the total heat through opaque part is 6.2 kilowatt. Equipment sensible load, there may be a number of equipment like toaster, heaters, tube lights, computers, printers. So their load is 9.2 kilowatt. Equipment latent heat, some of the equipment they do contributes toward they do contribute towards latent heat also, like coffee maker, frying pans, right? So from these equipment, a little latent heat is also added into the room. Outdoor conditions are 37 degrees centigrade and 50% relative humidity. So we will locate the outdoor condition on the psychometric chart. On this axis, there is a dry bulb temperature, and these curved lines are relative humidity lines. So dry bulb temperature is 37 degrees centigrade and relative humidity is 50%. So 37 degrees centigrade and 50%. So this is going to be the outdoor condition. Now let us call it state A. So this is going to be the outdoor condition. Now let us take inside condition also, that is 27 degrees centigrade temperature, that is dry bulb temperature, 27 degrees centigrade dry bulb temperature and 55% relative humidity. So 27, this is 50 and this is going to be the 55, between 50% RH line and 60% RH line. 27 degrees centigrade dry bulb temperature, this is going to be the state B. So this is outside air condition, this is the condition inside the restaurant. The air which is getting infiltrated into the system shall attain this temperature, and this infiltration bring in certain latent heat and certain sensible heat as well, right. In order to find the sensible heat and latent heat, we need to have mass flow rate of air which is coming into the room. So already we have volumetric flow rate, and this volumetric flow rate, when it is divided by specific volume, this is volumetric flow rate, and when it is divided by specific volume of air which is entering the room, we will get the mass flow rate. So mass flow rate is 117.9875 divided by specific volume of air at outdoor condition. Now outdoor condition, the specific volume here it is 0.90, this is 0.90 meter cube per kg line, and this one is 0.91 meter cube per kg. So this is going to be approximately 0.9075 meter cube per kg. This is liters per second, so this has to be converted into meter cube per second. Meter cube per second of air which is coming into the room divided by meter cube per kg of air. So this expression will give 0.13 kg per second. So the air which is getting infiltrated into the room is 0.13 kg per second. Now latent heat and sensible heat associated with this mass flow rate shall come into the room in form of infiltration. So sensible heat Q infiltration sensible is equal to mass flow rate of air. Sorry, we will get it directly from here. We need not do this. We will be getting directly from here, because here enthalpy is already given. So enthalpy is already given, enthalpy at A and enthalpy at B. We can take from this chart, and there is another point C, enthalpy at C we will also take from this chart. So enthalpy at A is, let us try to find enthalpy at A. Enthalpy at A is this one, this is enthalpy at A is 89 kilojoules per kg of air. HB, now HB is this one 59, HB is 59 kilojoules per kg of air, and HC first I will have to locate point C on this chart. This is point C, this is point C, and at point C it is 69. So HC is 69 kilojoules per kg. Now sensible heat which is coming into the room, this is QIS is equal to mass flow rate of air, infiltration air, multiplied by HC minus HP. So mass flow rate is 0.13 kg per second, HC is 69 kilojoules per kg, minus HB is 59 kilojoules per kg, and that is going to be equal to 0.13 multiplied by 10, 1.3 kilowatt, because kilojoules per kg, this is kilojoules per kg, and mass flow rate is kg per second. So kilojoules per kg multiplied by kg per second will give kilojoules per second, and that is going to be in terms of kilowatt. So the heat which is coming into the room is approximately 1.3 kilowatts as a sensible heat. Now regarding latent heat also we can do calculations. QIL, latent heat is mass flow rate multiplied by HA minus HC. Mass flow rate is again 0.13 kg per second. HA is 89 kilojoules per kg and HC is 69 kilojoules per kg. Now this is going to be 0.13 multiplied by 20 or 2.6 kilowatts. So we will write here, infiltration sensible heat is 1.3 kilowatt and infiltration latent heat is 2.6 kilowatt. If you look at this, the total heat is coming into the room is 3.9 kilowatts through infiltration. It is almost 1 ton of cooling is required for this only. So 1 ton of cooling will be required for cooling the infiltration air from this point to this point. Now we will make a table for sensible heat and latent heat. So in order to make a table on sensible heat and latent heat, first of all infiltration, sensible heat, and this one is latent heat. So through infiltration the sensible heat is 1.3 kilowatt, this is in kilowatts, this is also in kilowatts, and latent heat is 2.6 kilowatt. The second is solar heat gained through glasses. So solar heat gain through glass is 2 kilowatt. So this is going to be 2.0 kilowatt, that is sensible heat. Total heat through opaque part is 6, because opaque part there is only sensible heat transfer. The radiations are falling on the outer wall of that building and wall is getting heated up right, and that heat, the heat which is absorbed by the wall is subsequently transmitted to the room. Because outside temperature is high, inside temperature is low, so there is a transmission of heat from ambience to the room through different opaque parts of the building. So this heat is 6.2 kilowatt. Equipment sensible heat that I have already explained you, that is 2.9 kilowatts. Equipment latent heat is 0.7 kilowatts. And the restaurant has 100 chairs. There is a seating arrangement in the restaurant for 100 persons to sit. And as you know, when we are sitting in a room, we also emit certain amount of heat, and when person is not doing anything, I mean just sitting on the chair, then sensible heat addition to the environment is of the order of 100 watts. It means if 10 persons are sitting in a room, they are already contributing 1 kilowatt heating to the room. So here the sensible heat per person is 100 watts, maximum capacity is 100 watts. So let us go for the maximum capacity, the restaurant is full. So when the restaurant is full, then 100 kilowatts multiplied, 100 watts multiplied by 100 watts, and that will give 10,000 watts or 10 kilowatts. So, sensible heat addition to the room is 10 kilowatts by occupants. Latent heat per person. So, latent heat per person is 40 watts, 40 watts. So, that is going to be equal to 4000 watts or 4 kilowatts. So, each person is contributing latent heat equivalent to 4 kilowatts and sensible heat 10 kilowatts, altogether 15 kilowatts. So, approximately it comes around 2.5 tons of cooling will be required for dissipating the heat contributed by the occupants. Now, sensible heat per employee, because employees are moving here and there. So, heat liberated by the employees is more than the person who are occupying the seats in the restaurants. So, each employee is contributing 130 watts, and there are 15 employees. So, 15 into 130 divided by 1000, and that is going to be equal to 1.95 kilowatt. So, sensible heat added by the employees of the restaurant is 1.95 kilowatts. Now, latent heat. Latent heat by the employees is 80 watts. So, again 15 into 80 divided by 1000. So, it is going to be equal to 1.2 kilowatts. I am dividing this expression by 1000 just to convert watts into the kilowatts. So, it is 1.2 kilowatt. Sensible latent heat added from meals per person. Now, the meals which is served to the occupants is also contributing towards sensible heat and latent heat. Restaurant is fully occupied. Suppose 75% of the occupants are taking food and 25% are waiting for their food. So, now what we can do here, 75% are taking food multiplied by 170 divided by 1000. This will be the sensible heat added by the food, that is going to be 75 170 divided by 1000, 12.75 kilowatt. So, 12.75 kilowatt is the heat, sensible heat added by the food. Now, latent heat, it is 120. So, 75 into 120,000, that is 9.0 kilowatt. So, now we have, I think, all the load on the building, that is due to infiltration. 2 kilowatts is coming from fenestration, direct solar radiations. 6.2 by opaque part of the building, walls, ceiling and the floor of the building. 2.9 and 0.7 are coming from the equipment in the restaurant, sensible heat and latent heat. 10 kilowatts occupants load, 1 point and sensible load, and 4 kilowatt latent heat load, and 1.95 kilowatt is coming from the employees as a sensible heat and 1.2 kilowatt as a latent heat, and this 12.75 and 9.0 kilowatt is for sensible heat added by the food and latent heat added by the food respectively. Now, what we can do now, we have to calculate the total load. So, the total load is sum of sensible heat load, that is 1.3 plus 2.0 plus 6.2 plus 2.9 plus 10 plus 1.95 plus 12.75. It is 37.1. Right. Now, you can also do calculation along with me. So, if there is any mistake, you can identify. Oh, this is nil. Now, here latent heat load is 2.6 plus 0.7 plus 4 plus 1.2 plus 9.0, and that is equivalent to 17.5. That is latent heat. So, latent heat load is 17.5, sensible heat load is 37.1. So, the total load is in the building is 37.1 plus 17.5, and that is going to be equal to 37.1 plus 17.5, 54.6 kilowatt. Now 54.6 kilowatt is the cooling load in the building. Suppose I ask you to find the tonnage of AC plant. So tonnage of the AC plant you can immediately find just by divide by 54.6 by 3.5, and you will get 54.6 divided by 3.5, 15.6 tons of refrigeration. Now 54.6 plus divided, yes, 15.6 tons of refrigeration, or you can recommend a 50-ton capacity plant for this restaurant. So in this case, sensible heat is 37.1 kilowatt and latent heat is 17.5 kilowatt. Now next thing we are going to do, we will find the sensible heat factor. Now the sensible heat factor is sensible heat divided by total heat, and sensible heat here is 37.1 divided by total heat is 54.6, and this will give the sensible heat factor as 0.68. Now in this case the sensible heat factor is 0.68. In this chart, in the psychometric chart, there are certain marks here. These marks are for these marks show the sensible heat, the ratio of sensible heat and total heat, that is sensible heat factor, and these marks are starting from 1 to 0.3, which covers all type of indoor environment. Now 1 means sensible heat factor 1 means there is no latent heat. So that is going to be a horizontal line, and this horizontal line is going to be like this, because if I want to have, suppose in this case the sensible heat factor is 0.68. So 0.68 is going to be here, 0.65 and 0.7. Between these it is divided in 5 parts. So the last one is 0.68. This one, second last, is 0.68, and this 0.68 is joined with the ideal condition, that is 24 degrees centigrade. There is a circle here, so this point has to be joined with this one. This is sensible heat factor line for, this is a sensible heat factor line for 0.68. So I am repeating. First of all, we identified the 0.68 mark here, and that 0.68 mark is connected with this small circle, center of this small circle that depicts 24 degrees centigrade temperature and 50% relative humidity. So we are getting this line. It is going to be this line, right? There is another way also for drawing this line. There is a half circle here. The inside marks of the half circle show the ratio of sensible heat and total heat, that is sensible heat factor. So here also I can locate 0.68, that is going to be like this, 0.68. And any line parallel to this line will show the sensible heat factor of 0.68. So these, in fact, these line and this line, they are parallel. So you can choose either of the way. Either you choose these marks, or you choose this half circle, you will be getting the same results. So this is our sensible heat factor line, and this line now room condition is this, right? So a line parallel to this line passing through this point will give the sensible heat factor line passing at the room condition. So what we will do, we will draw a line parallel to this line passing through the inside room condition. So that is going to be this line. So this is cutting this line at 13 degrees centigrade. Now this is your inside design condition, right? And this is your sensible heat factor line. It is also stated here that the minimum temperature of air supplied to the room is 17 degrees centigrade. So air which is supplied to the room is at 17 degrees centigrade. So this is 15, 17. So we will draw a vertical line because we do not know the location. We will draw a vertical line from 17, and this is the state. This is the state from where the air is supplied to the room. Let us say this state is D. Now air is entering the room at this state, that is approximately 85%, and it is leaving the room. It is leaving the room at this temperature, that is 27 degrees centigrade dry bulb temperature and 55% relative humidity. And this is the load line. This line is known as load line. So all the cooling load here, all the load in the room is heating in the room is taken away by this air. So in order to find how much air has to be shall be required for cooling, for the purpose of cooling in this room, we can use this total heat, this one 54.6. So 54.6 is equal to mass flow rate of air multiplied by HB minus HD. HB minus HD. Now HB is already we have taken 59, and HD is approximately 41.5. It is so HD is 41.5 kilojoules per kg, and HB is already we have calculated, that is 59.0 kilojoules per kg. So 54.6 is equal to mass of the air multiplied by HD, HB minus HB, yes, HB, that is 59.0 minus HD, that is 41.5, and in this case we will get a mass flow rate of 54.6 divided by 59 minus 41.5, 3.12 kg per second, right? Fresh air available is 4000 meter cube per hour. Outside air, the outside air which is coming in, so mass of the air we will write here, mass of the air is 3.12 kg per second, which has to be circulated inside this room. Now fresh air is 4000 meter cube per hour, and if we convert this into kg per second, again 4000 divided by 3600 multiplied by specific volume of air at state 1, that is 0.9075, and this will give in kg per second, mass flow rate in kg per second, and that is going to be equal to 1.224 kg per second. Now this much of mass of air is available outside, but we need 3.12 kg per second. Where from the gap will come? The gap will come through recirculation of air inside the room. The air which is leaving the room, it will be mixed with the outside air, and this mixture will be circulated inside the room. So here in this case, outside air is 1.224 kg per second, total air is outside air, or total air is required 3.12 kg per second. So percentage of, or the part of outside air which has to be circulated in the room is approximately 0.392, that is the ratio of m out divided by m, or 1.224 divided by 3.12. Now how to take this mixture? Now for taking the mixture of outside air and inside air, we will join these two lines. We will join these two lines. We will join these two lines, and we will take 0.39. So this part will be 39.2, and this part is going to be 70.8. And in this ratio, if we take the values, so we will be getting somewhere here. This is point E. So this is 0.392, and this part is 0.608. So this part is 0.608, and this part is 0.392. And this mixture of fresh air and return air, they will enter the room, and yes. So this is the room supply condition. So they will be entering the room. So we will draw. We will connect these two lines. So outside air, now the arrangement is like this for the air conditioning of this restaurant. Outside air is taken, and it is mixed with the recirculating air in the ratio of 0.392 and 0.608. Now this mixture enters the cooling coil, and enters the cooling coil, or it passes over the cooling coil and attains the temperature of 17 degrees centigrade. Then air is supplied to the room. It picks from the heat from the surroundings, and the air which is leaving the room is at 27 degrees centigrade and 55% relative humidity. Now for the circulation of air inside a room, a fan is also provided. Now there are two situations. Either fan is provided before the cooling coil and after the cooling coil. If fan is provided after the cooling coil, then it becomes the part of the load in the system, then it will be added to the sensible heat. So the heat provided by the fan or heat added by the fan shall become a part of the sensible heat, and again we will have to calculate sensible heat factor. Now if the fan is provided before the cooling coil, in that case sensible heat added by the fan shall be added here, and in that case this will become the line for cooling of mixture of air. That is all for today. In the next class we will be taking air distribution system inside a room. Thank you.